Let's look at some examples of gas about graphs. Now, read question number 1. Let the initial constant temperature of the gas be T1. The graph is the PV graph for the constant temperature of the gas T1. By equation of state, we can write down PV equal to nRT. The initial temperature, which is constant, is T1, therefore PV equal to nRT1. For part A, if the constant temperature of the gas increase to, for example, T2, then we have PV equal to nRT2 with T2 larger than T1. Because T2 is larger than T1, that means the product of the pressure and the volume increases. That is, the final PV is larger than the initial PV. That is, the new graph will become a new curve, which is higher than the previous one, with temperature constant, which is T2. For part B, if the vessel contains a greater mass of the same gas, that means the number of moles of the gas increases. Therefore, we have the new graph becomes PV equal to n pi RT1. But n pi is larger than n. The number of moles of gas increases because the mass of the gas increases. As a result, the product of PV is larger than the product of PV in the initial temperature T1. Therefore, the new graph will be also higher than the previous one, for example, this one, for n increases. Now study question number 2. By using the equation of state, we have PV equal to nRT, or P equal to nRT over V. For constant temperature, T, and fixed mass of gas, that means the number of moles of gas is also constant, we have the pressure of the gas is proportional to 1 over V. The graph of P against 1 over V is a straight line passing through the origin, and the slope of this graph is equal to nRT. For another vessel containing the same mass of ideal gas, that means the number of moles of gas is the same, but the temperature is higher. That means T increases to a higher value. Therefore, the slope of the graph nRT will increase because the temperature increases. As a result, the new graph will be a straight line passing through the origin with greater slope. For example, this one. Now study question number 3. For part A, the absolute zero temperature can be found by extend the temperature axis backward and produce the straight line backward. When the straight line passes through the point on the temperature axis, then this temperature is called absolute zero temperature. We call T0, for example. The slope of the graph is constant. Therefore, we have 210 minus 150 over 100 minus 0 equal to 150 minus 0 over 0 minus T0. Therefore, the absolute zero temperature from the experiment is equal to negative 250 degrees Celsius. Let the temperature at which the pressure is 180 kilopascal be T. We can use the slope to find T. For example, 210 minus 180 over 100 minus T equal to 210 minus 150 over 100 minus 0. Therefore, the temperature is equal to 50 degrees Celsius. Now take some time to study question number 4. By using equation of state, we have PV equal to nRT with temperature T in Kelvin scale. That is P over T in K equal to N R over V. And the slope of the straight line is equal to N R over V. For another gas bulk B of greater volume, that means V increase, containing the same mass of gas, that means the number of mole of gas remain the same. That means the slope of the graph, because V increase, therefore the slope of the graph equal to nR over V will decrease. Hence, the new graph will be a straight line passing through the origin with a smaller slope like this one. For the graph of P against temperature T with temperature in the scale of degrees Celsius, since the absolute temperature, the absolute zero temperature remains the same at this point, therefore the new graph will be a smaller slope like this one, but with the same absolute zero temperature. Therefore, the new graph will be like this one. You must notice that even though the volume change or the mass change, even though, but the position of the absolute zero temperature must remain the same at this point. Now study question number 5. By equation of state, PV equal to nRT, temperature T in Kelvin scale, TK. Okay, we have V over T equal to nR over P. For the graph of V against T in K, it is a straight line passing through the origin, and the slope of this graph is equal to nR over P. If the experiment is repeated at a smaller constant pressure P, that means the gas pressure decreases. The constant pressure is smaller. That means P decreases. Hence, the slope of the graph will increase by decreasing p. The slope will increase. Therefore, the new graph will be a straight line passing through the origin with greater slope like this one. For the graph of V against temperature T in the scale of degrees Celsius, the position of the absolute zero temperature remains the same at this point. Therefore, the new graph will be again a straight line with greater slope but passing through the same x-intercept, will be like this one. For question number 6, in each of the following graphs, complete the blanks by using greater than or smaller than symbol. For the first one, using PV equal to nRT, we say T1 is larger than T2. For the second one, using PV equal to nRT, we have V over T equal to nR over P. Therefore, P9 is smaller than P10. For this graph, by PV equal to nRT, we have P over T equal to nR over V. Therefore, V7 is smaller than V8. For this one, we have PV equal to nRT. Therefore, P equal to nRT times 1 over V. Therefore, we have T3 larger than T4. For this graph, P against T in degrees Celsius, you can compare with this one. P against T in Kelvin temperature. The slope of graph 7 is larger than that of graph 8, and the slope of graph 5 is also larger than that of graph 6. Therefore, we have V5 is smaller than V6. For this graph, V against T in degrees Celsius, you can compare the graph with the graph of V against T in Kelvin temperature. For this one, since graph of line, the slope is higher. Therefore, for this one, graph 11, the slope is also higher. By comparing these two graphs, we have P11 is smaller than P12.